Fixing the Defect by Team Grant. Team Members' Contributions by Team Grant. Brian Pinson, slides 3 through 8. Paul Hafer, slides 9 through 14. Patrick Minette, slides 15 through 21. Zachary Williams, slides 22 through 28. From defect to failure, how a defect becomes a failure. First, an error in the source code causes a defect. Ultimately, the defect is created by the programmer. Then, when the program is executed, the defect will create an infection, which means after the execution of the defect, the program state is different from what was intended. The infection will propagate. Infection can spread as functions are fed erroneous inputs, and later program states become infected as a result. Eventually, the infection causes failure. Failure is an externally observable error in the program behavior. It is caused by an infection in the program state. In this example, we can see how erroneous code causes the sane state to become infected. The next state contains more error, and as a result, it creates an infection chain. If a defect is found, first track the problem and then reproduce the failure. Try to automate and simplify the test case. Find possible infection origins. Focus on the most likely origins, such as known infections, causes in state, code, and input, anomalies, code smells. Then isolate the origin of the infection and correct the defect. In this example, we see a problem where the program is sorting integers and is printing out different numbers. We can try to re-enter last output to reproduce the failure. Find origin by breaking the program down into its two functions, main and shell sort. After testing shell sort and not finding an error, the problem exists in main, which is feeding shell sort with erroneous information. The origins of the infection is isolated in line 36, which accidentally confuses the number of arguments with the number of numbers to be sorted. Techniques for locating defects. Infections are best found using assertions. Causes look for invalid inputs that cause crashes. For dependencies, some variable is dependent on another. For abnormalities, look for some code that executes or function calls only during a failing run. Look at the variables and if they have abnormal values during a failing run. For code smells, look for uninitialized variables, unused values, and unreachable code. How to integrate techniques for locating defects. First, find the starting point where the program fails. Follow the dependencies. Assert an invariant and observe the state. Follow the chain of anomalies until the source is found. Focusing on errors. Assertions ensures data sanity over a long moment in time and a wide range in space. Any failing assertion by definition signals an infection. Anything covered by a passing assertion is no longer needed to be considered. Anomalies. Aspects of the execution, the properties of which correlated with failure, such as coverage or dynamic invariant. Causes. Aspects of the execution, such as input state or code, that are not only correlated with failure, but experimentally proven to cause failure. They are more likely to indicate the defect than the anomaly. Focusing on errors. Infections, if the origin is already known to be faulty from a failing assertion or by observation, make this top priority to investigate if the infection causes failure. For causes, if some form of experimentation, such as delta debugging, has highlighted some state or input causing failure, check if they are infected and causing failures. Origins associated with anomalies are more likely to contain errors. If code smells are detected in the program, and if one is of possible origin, first investigate if the code smell causes the infection. For dependencies, anything that is not a backward slice of the infected state cannot possibly have caused the infection. Of all possible origins, check the backward slice for infections, starting with the closest statement.
Now we're going to talk about some of the techniques that we went over. The first one being dependencies. So X represents the infected value, and the failure is due to this infected value. On this value, we could zoom out a little bit and have this be more modular. So we could break down the code into chunks, and that could be the infected chunk of the code. And so we're going to examine the source code, looking for other variables or modules of the code that could determine the possible origin of the infected value. So if we look at the image here on the right, we can see the exclamation points represent the possible origins of the infection. And we're going to create a table with these dependencies. And then we're going to trace the dependencies backwards until we find the origin of the infection. The next technique is using observation. What we should do is observe each of the origins and check if that value is infected. If the value is infected, we need to check the dependencies of that value and determine if its dependencies are also infected. So we'll continue following these dependencies and observe until we find an infection that has sane origins. Now the problem with this is this could take a long time, depending on how many dependencies there are and how many possible infected origins there are. So, to help us save time, we're going to use observation along with induction and experimentation. So if we look at the picture here on the right, we can see that we don't have to worry about those exclamation points on the right hand side that are grayed out right now, because we found an infection, which is that blue X that is circled. For now, we will worry about the dependencies of that variable. Our next technique is assertion. Assertion can be defined as a confident and forceful statement of fact or belief. Now we can use assertions and they can be very helpful for us. Any failing assertion signals an infection. Assertions are used to guarantee that the state is sane. So for now, we can ignore the possible infected origins that pass assertions. As we can see here, these marked with a check mark and circled are those that passed the assertions. So once again, we don't have to worry about those for now. Now it should be noted that although some of these are passing right now with assertion or observing the dependencies and all the other ones that we've talked about thus far, that does not mean that they are free and in the clear. We may have to go back and check them at a later time in case our bug is not related to one of the other bugs, or the bug that we fix could potentially cause another bug. Another technique is looking for anomalies. An anomaly is something that deviates from what is standard, normal, or expected. It's best to start with examining anomalies, since they are often the ones correlated with failure. If it has abnormalities, it reveals an infection. So we can see here the variable that is circled, the X, is an anomaly. So we're going to check the dependencies of that anomaly and not worry about the ones that are just to the left of it for now. The last technique is the cause transition. Causes are aspects of execution that are experimentally proven to have caused the failure. These are proven with experiments, not necessarily mathematically. Causes have a better chance of helping us to find the defect, even more so than anomalies, since anomalies are just often correlated with the defect. Causes are proven to have actually caused the failure. So the cause transition is a statement that causes the failure. So the origin is sane, but the target is infected. So here's the defect. Now this could be something wrong with the logic in the code, such as you have a variable go in as one of the arguments and you do some manipulation to it, and the output is not what you expect it to be. And that is what needs to be fixed. And then using the cause transition, we complete the infection chain. So now we see that we started with the failure at time 8, and we traced backwards until we kept finding more failures, that the state was not sane, and we went all the way back up, and then we found the cause, and then we see the check mark represents a sane state, and the X is the failure. After we fix the statement that caused the failure, we need to test our code again, as there may be other bugs that were not found, or this fix could have released some other potential bugs. So we've learned about these techniques, but what one should we start with first, since we don't want to spend all of our time just performing every technique one right after the other until we find the defect. So the first step would be to read the code, see if anything jumps out at you. Reading the code will also help you understand what's supposed to be going on. If it doesn't jump out at you, the next thing you could do is focus on infections. If we know an origin is faulty, we should focus on that origin first. This should be common sense. The next step would be to focus on causes. Since causes are experimentally proven to have caused the failure, we should focus on the failure cause. This could be found via delta debugging or other experimentation process. The next thing we should do is focus on anomalies. Since anomalies are often correlated with failures, this is another good place to start. Given a set of origins, the ones with the anomalies have a higher chance of containing errors. And then the next thing to do would focus on code smells. If you have code smells, and it is one of your possible origins, you should check those. Code smells could be anything from an uninitialized variable to just a weakness in the actual structure of the code. The next thing to do would be focus on dependencies. For all of the origins, check the backward slice for infections, starting with the closest ones. But as we have seen before, this could take a very long time.
Tracking infections. If you need to track down which origin, we can use the earlier mentioned techniques such as traffic or automated ones. We don't need to identify every bit of the infection chain, since we just want the origin. We can put larger gaps where communication is restricted, which makes it easier to assess the sanity of a state. If we find some state that is sane, we can disregard the earlier states and only search forward to find an infected one. Once we find the transition from a sane state to an infected one, this is our origin. Is the error a cause? We have to show causality for an infection origin so that we know we are on the right track. The program on the right outputs a equal to 0, and we assume that the function creates the infection. However, we have not shown that a being 0 causes the program to output 0, and if we were to change it, would it still output 0? Is the cause an error? We can fix our program to make the failure no longer occur, but our program can still fail nonetheless. We have to look to fix the cause rather than the symptom or instance of the problem. In the example on the right, the problem still occurs but is corrected for 1, 2, 3. Debugging into existence. In the coding example prior, the fix would be the header for the for loop, since it is accessing an out-of-bound exception, and thus the header should be fixed to correct the cause rather than the symptom for 1, 2, 3, since it may occur for other accounts. Fixing code to make it work for one case doesn't fix it for every other possible cause, and can be forgotten or left behind for later. The fix that was implemented doesn't help understand why the bug is occurring, and thus could lead to more down the line on top of not fixing the current coding problem. Devil's Guide to Debugging. Things not to do. Finding the defect by guessing. You don't want to scatter debugging statements throughout the program, or changing the code randomly until something works. Be sure to back up old versions of your code in case something happens, and you want to try to comprehend what the program is doing. You don't always want to use the most obvious fix, at least in the example that was provided, where if y equaled a specific value, they just automatically set the value for x, rather than making it work as intended. Correcting the defect. Does the failure no longer occur? After correcting the code, make sure that the failure no longer occurs. This validates causality and verifies that we solved the problem. Determining success is easy to check if you try to replicate the problem like before and it doesn't occur. If it fails, then it might not have been the right fix, or it may have created a new problem. Did the correction introduce new problems? This can be very difficult, since most corrections cause new problems. Have corrections peer-reviewed to help check if new bugs occur. Also, having a regression test ready can help spot unwanted behavior changes. Note, only try to fix one defect at a time, as multiple fixes can affect one another. Was the same mistake made elsewhere? The defect you have corrected may have been a mistake that may have been made elsewhere in the code. One example is not allocating enough characters for an array, since the null character is often forgotten, hence why the string dup function was created for malloc of string length string plus 1. Did I commit the change? It is important to commit changes to the production code with the fixes and assigning a resolution to the problem. Logging with a message for the fix and bug is also a good to help others see your changes, as well as being able to be used for a future fix.
In some cases, locating a defect is not difficult, but correcting the defect is. The following are some reasons this might happen. Unable to change. The program in question cannot be changed, for instance, because it is supplied by a third party and its source code is not available. Risks. The correction induces huge risks because it implies large changes throughout the system. Flaws. The problem is not the code, but in the overall design. That is, the system design must undergo a major revision. Famous workarounds. Spam filters. Workaround for solving a flaw in the email system. Anyone can forge arbitrary messages and conceal his or her true identity. The proper solution would be to redesign the entire email system, even incurring all associated costs and risks. Virus scanners. Workaround to what is a flaw of some operating systems. By default, every user has administrator rights, and thus any downloaded program can gain complete control over the machine. The proper solution would be to assign users limited rights and ask them for proper authorization before attempting to change the system. Date windowing. Workaround to the inability of many legacy systems to deal with 4-digit years. The systems still keep 2-digit years and resolving ambiguity by defining a 100-year window that contains all years in the data. The genuine solution would be to adapt the legacy system, but doesn't account for costs and risks. Learning from mistakes. Mining the past. Generally, past defect data are easily obtained from existing sources. Check the version archive. The version archive will have records of all changes to the system. Check for changes in maintenance branches. Once a product is released, many organizations create a dedicated maintenance branch off of the main versioning trunk, a branch in which only fixes to the released product are committed. Advantages: provides precise information without requiring a problem database. Disadvantage: requires discipline and effort to set up and keep up the standards. Check the message log for keywords. A simple way to identify fixes is to just check the log system for keywords such as fix, bug, problem, defect, crash, and so on. If one of these keywords appears in the log message of a change, then the change is likely a fix. Where do defects come from? There are 3 important stages in the development process that all can introduce defects. Specification. What is it that makes a specification error-prone? Programming. What is it that makes it hard to translate a specification into a correct program? Quality assurance. How can quality assurance fail to catch the defect? Errors during specification. When analyzing defects, assess whether they were introduced during the specification phase. If you find that several defects are due to the specification issues, here are measures to take. Improve quality assurance. Introduce systematic processes for eliciting requirements in software design. Check specifications early. The earlier you check against the requirements of your clients, the more precise the requirements will become. Increase the precision. Introduce semi-formal or formal methods that allow you to catch the inconsistencies or incomplete specifications early. Increase the degree of automation. The more development tasks you can automate, the less chances there are that the humans involved make mistakes. During programming. Improve programming as you improve specifying. A complex specification always translates into a complex program. Do anything to make the specification more precise, complete, or better validated. Reduce complexity. The higher the structural complexity of a program, the more ways there are for some part of the program to influence another, and the easier it is for infections to spread. Improve documentation. When writing software, write for humans just as well as you would write for the machine. Documentation should be thorough and precise. Change your programming language. Most features in the new programming languages are designed to avoid the programming errors as experienced by the users of older programming languages. Recent code changes before release need a special focus because code changed at the last minute may not be as thoroughly tested as older code. Errors during quality assurance. Quality assurance is needed to catch defects before escaping into production. To keep them from failing, some precautions can be made. Test early, test often. The earlier you test, the more precise your specification will be, and the more you test, the more defects you will catch. Improving test suite. The test suite must be extended such that the problem will not occur again. Your extension should not only test for the particular problem, but also for related problems. Improve your analysis tools. Verify whether common tools could have detected the defect early, tools that detect code, or tools that verify system assertions.